A distinctive feature of the vacuum system used for nucleotron-type magnets is that it includes two vacuum volumes: a vacuum volume with a beam chamber, where a charged particle beam is actually accelerated, and an insulating vacuum volume, where liquid nitrogen pipes, helium pipes, and a heat shield are located. The latter reduces the heat stream toward the magnet by means of warm cryostat radiation. The requirements for the vacuum in the beam chamber and that of the insulator vacuum volume are completely different. For the insulator vacuum volume, it is enough to remove the atmosphere to avoid convective heat transfer. It corresponds to a pressure level of about 10 to the power of -6 torr, which is achieved with the use of ordinary oil evaporation pumps. At the Nuclotron, for instance, the pumps being used were inherited from the synchrophasotron. I will tell you more about the requirements for the vacuum in the beam chamber later, as it is much more complicated. Insulating chambers and beam chambers are pumped out with either turbomolecular or non-evaporable getter pumps. The feature of a superconducting accelerator vacuum system is that the vacuum chamber in the magnets is at the temperature of the liquid helium, and all heavy gases freeze in this vacuum chamber. This means that the magnet itself serves as a heavy gas pump. The main component of residual gas is hydrogen molecules, which are pumped with turbomolecular or getter pumps. In a superconducting magnetic system, where the vacuum chamber is at the temperature of the liquid helium, rather serious problems are posed by not only the production of the vacuum, but also by the manner in which it is measured. All vacuum meters are at room temperature and are located in the pipes outside the cryostat. Accordingly, they measure the pressure in the chamber, but not in the beam chamber itself, rather in the pipe connected to the beam chamber, but located quite far from the chamber. It's not always easy to recalculate the pressure indicated by a vacuum gauge when referring to the residual gas pressure in the beam chamber. The most precise instrument for measuring a vacuum in a beam chamber is the accelerated particle beam itself. For such measurements, for example at the Nuclotron, the magnetic system is powered by a constant current, which are highly stabilized in order to eliminate the influence of the noise of the magnetic system on the lifetime of the beam. As a test case, a beam with a known loss cross-section resulting from its interaction with residual gas is used. For example, a magnetic system is tuned for deuteron acceleration. Positively charged hydrogen molecules are used to measure the vacuum. They have the same mass and the same charge. That is why, with some minimal adjustments, it is possible to secure circulation of such molecules in the constant magnetic field. The cross-section of the dissociation of such molecules on residual gas is well known. For example, the cross-section for nitrogen atmosphere is 1.5 times 10 to the power of -16 square centimeters at 5 megaelectron-volt of beam energy, which is in line with the injection energy. The graph demonstrates the dependency of beam intensity on time. It is described with an exponential relation. The characteristic time is the residual gas density multiplied by the cross-section and particle speed. By approximating the exponent dependency, it is possible to define the residual gas density in a vacuum chamber. This is exactly how the measurements are performed when a calibration of vacuum detectors is needed, which are at room temperature. In heavy ion synchrotrons, and in the synchrotrons that ensure high beam intensity, problems arise with altering the residual gas pressure during the operation of an accelerator besides the challenge of obtaining a vacuum in the beam chamber. They are the so-called problems of a dynamic vacuum. One of them is caused by the fact that, during the supply of a magnetic field cycle, in case of a fast increase of Foucault currents, the vacuum chamber walls heat up, and some of the gas that had been frozen on the walls of the vacuum chamber melts and flows inside the chamber. At the beginning of an accelerator operation, through vacuum fluctuations, it is possible to restore with a very good accuracy both the amplitude and the main time parameters of the magnetic field cycle. This effect slowly dies out as residual gas gets pumped out by the main pumps. The other problem related to dynamic vacuum and dynamic vacuum alteration is the loss of heavy ions through their interaction with residual gas ions. A heavy ion may either capture or lose an electron. In this case, the trajectory of its movement in the magnet changes, and it falls on the wall of the vacuum chamber. In doing so, it may knock several thousands of new molecules off the vacuum chamber wall, which in turn would enter the vacuum chamber. As a result, the pressure inside the vacuum chamber rises, the amount of lost heavy ions increases, and the chain of positive feedback closes, causing the so-called vacuum instability. The beam, due to the initially small losses in vacuum, deteriorates the vacuum itself. This leads to an increase in the loss. The beam is therefore killing itself, and it is killing the accelerator vacuum. To avoid such negative effects, it is necessary to use a collimation system of lost particles in heavy ion synchrotrons. This entails the placement and localization of loss points in specially designated areas where a particle receiver for reducing gas separation can be prepared, and to engage additional pumping instruments in order to remove the stream of separating gas. Among other things, it is necessary to specially prepare the walls of the vacuum chamber. It is also needed in case of another problem arising related to vacuum instability. This problem is related to electron clouds. The circulating beam of accelerated charged particles leads to ionization of residual gas molecules. The emerging electrons, under certain conditions, may accumulate inside the vacuum system, which may cause the diagnostics to fail, or may lead to a shift in the frequencies of transverse ion oscillations and to the destruction of the main beam. To avoid this, one needs to provide the vacuum chamber and the surface of the vacuum chamber with a small coefficient of secondary emission. After resolving all the problems with the vacuum chamber in the insulator vacuum volume has been attained, and the cooling of the magnetic system can now begin. Cooling of the magnetic system is a task for the cryogenic supply system. The cryogenic supply system provides the magnetic system with liquid helium and liquid nitrogen. Accordingly, an instrument that liquefies helium and nitrogen is needed. And in the best case, if we want cost-effective operation of the facility, we need a system for the recondensation of liquid nitrogen and helium. The Nika complex will have several superconducting facilities. Besides the existing Nuclotron, it will have a booster and 2 collider rings, together with superconducting detector magnets. Consequently, the cryogenic complex should ensure the removal of the warmth from all of these devices. The basis of the cryogenic complex is the liquefied helium inside the facility. At the moment, the cooling capacity at liquid helium temperature of our helium liquefiers amounts to about 8 kilowatts. Our helium station is the largest in Europe. Commonly, helium and nitrogen cryogenic systems include many elements, which are schematically outlined on the map of our complex. After the accelerator is cooled down, the testing of the quench detection system begins. How has this system been incorporated at the Nuclotron? When current flows through the Nuclotron magnets, they are impacted by the voltage due to the inductance of the magnets. This voltage is equal to the derivative of the current multiplied by the inductance. With a high rate of growth, this voltage can amount to about 300 volts. Besides that, additional voltage appears as a result of the magnetic reversal of the magnets, due to the whirling currents in the coils. Additional voltage may occur if one of the coils accidentally changes into a normal conducting phase, while there is active resistance on this coil. This extra voltage on a magnet needs to be detected by the quench detection system. The voltage has a value at the level of hundreds of volts of inductive voltage. To identify this value, two neighboring magnets are connected with a bridge joint. The coils of these magnets form a bridge. The bridge is being balanced. As a result of the flow of the same current through these magnets, the system does not detect any inductive voltage loss. With the emergence of a normal conducting phase, the bridge loses its balance. The off-balance signal is the signal for the emergency evacuation control system and the supply system to switch off the main source. The quench detector has to satisfy quite a few requirements. Firstly, the supply system must not cause any interference with the power system. Secondly, the detector has to be isolated, both from the main power supply and from the ground. And lastly, it has to offer a particular set of service functions. That is, to record the signals of voltage development during the occurrence of a normal conducting phase. The signal of activation of the energy evacuation system has to be given in case the off-balance current exceeds some threshold value, predefined by the operator, and in case the duration of this excess is longer than the predefined threshold time. For fine-tuning, the detector should allow remote control of these parameters. The Nuclotron has around 200 such detectors, pairwise connected magnets and quadrupole lenses. It is also protected by group detectors. There are few magnets that don't have a pair. To protect these magnets, a potential output of energy in the middle point of the coil is used. The bridge is formed from two halves of the coil of the same magnet. All these detectors are combined into a main control system, which, in case of a quench, shows the point of origin of the quench and provides insights into its developments. When a signal is transmitted from the quench detection system about a normal transition phase, the energy evacuation system gets activated. This chart demonstrates the fundamental elements and the main instruments that play a role in the process of energy evacuation. This is the inductive load, this is the accelerator powered by a current source, and the current source. Under normal operation of the accelerator, the current, which is supplied from a source to a load, flows through a power thyristor. When a normal transition phase is detected, a signal is sent to the commutation thyristor, and the energy that had been accumulated in a special capacity locks out the power thyristor, and the current is shifted to the chain containing field suppression resistance. The energy accumulated in the magnets dissipates in the active resistance of the field quenching resistor. At the same time, the main power supply disconnects from this network, and a short circuit occurs at the point of its connection. As a result, the energy accumulated in the magnets is ejected out of the cryostat and turns into warmth without causing any damage to the magnetic system. The magnetic system of the Nuclotron includes 96 dipole magnets and 64 structural quadrupole magnets, which are divided into several families in terms of their respective dependence on a power supply system. Dipole magnets have 4 families of magnets in terms of power supply. Furthermore, a separate family is made up of defocusing and focusing lenses. However, the size of these families is selected in such a way that each has approximately the same inductance. The current flows into each of the families through powerful current leads. Besides the main ring of the Nuclotron collider, the magnetic cryostat system of the Nuclotron also includes a measuring half period with magnets identical to those of the Nuclotron, which are used to measure magnetic strength. A part of the current lead is located on the measuring half period, and another part is placed exactly on the ring of the Nuclotron. The entire circuit comprises the main supply source that applies current into all the magnets successively turned on. To provide the required beam focusing, there are 2 additional supplies of lesser power, one of which performs the partial current removal from the successively turned on focusing and defocusing lenses, while the second applies additional current into the defocusing lenses. The main power supply provides current from 60 to 6,300 amps, with voltage of up to 300 volts. The rest of the power sources have less power. To control this entire set of instruments, the so-called cycle assigning equipment is used. To specify a field cycle, an operator from the control panel specifies the so-called reference function, which reflects the desired dependency of a magnetic field on time. This reference function is used to control the main power source. Apart from that, the operator specifies two current binding coefficients of the main power source, the source of current supplement and partial current removal. The current of each source, regardless of its design, must comply with the reference function. Tuning is done by means of a feedback system. As feedback system signals, either an indication of the magnetic field strength value of a measured period or the readings from current sensors of the corresponding chain may be used. For adjustments, proportional, integral, and derivative controls are used, known as PID controllers, which provide the required quality of the execution of a magnetic field cycle. On the operator's screen, there is a special window on the control panel where a reference function can be specified. From here, one can see magnetic field signals in dipole magnets and quadrupole lenses, the voltage and the current of all the power sources. After a cycle is adjusted, it is possible to inject a beam. Here, diagnostics comes into play. Diagnostics includes a lot of multifaceted devices. Operational characteristics of each instrument depend on what kind of parameters of the beam it measures. There are special beam position monitors. They are usually called pickup stations because of their design. They measure the center of gravity position of a particle bunch circulating in the accelerator. There are sensors that measure the current. As a rule, these are current transformers. To measure the beam size, the so-called profilometers are used. There is a profilometer mounted inside the ring of the nuclotron. It has to work by a non-destructive method, that is, it must not influence the beam parameters. There are profilometers placed in the injection channels and in the channel of the extracted beam to tune the injection and extraction processes. There are also more complex diagnostic systems. For example, measurement systems for the betatron frequencies, which include a number of tools. There is a loss monitoring system, and there are small-sized neutron detectors located along the accelerator ring. The signal received from them is proportional to the loss intensity in the given point of the ring. Our stochastic cooling system is used as part of the diagnostic system to measure the momentum spread